Keiryopackaging company, a material efficiency as a pathway towards a price competitive sustainability. And it will be introduced and presented by Tangui Van der Elst. And Tangui is a lawyer by training, and before starting Keiryo, he worked in public affairs for leading fast-moving consumer goods and packaging groups in Brussels and Geneva, focusing on sustainability and packaging regulation. Tangui will discuss how materials efficiency can be a pathway towards a price competitive sustainability, and he will explore how Keiryo's innovative polymer processing technology enhances material performance, which reduces both environmental impact and manufacturing cost. Keiryopackaging offers a scalable, low-cost solution that can be integrated into existing production assets, making it an exciting development in the pursuit of sustainable and cost-efficient packaging solution. By the way, and that's a very interesting information which I just got today, if you question yourself what Keiryo means, comes from the Japanese word for less weight, which is very appropriate, I should say. Tangui, please drive us through the presentation.
Yes, well, thank you, Roberto. Thank you for the introduction. As you mentioned in the introduction, I am a lawyer, so I can take no credit for the technology that we developed, but I do take credit for the name because we had to find a way to explain in a simple way, you know, what we were doing, which is basically generating materials efficiency. And if you have an efficient material, you can use less of it. And then we thought that Keiryo, a Japanese word, was an interesting way to reference what we were doing. So let me start with our presentation, Keiryopackaging. Just for the clarity, I will start with what we're not. We are not developing a new material. We are not developing an additive. We are developing a processing technology that increases the performance of polymers. And that's what allows us to claim that our technology allows to reduce the environmental footprint, but also the manufacturing cost of plastic packaging. And if you look at the big picture of what we are seeking to create, the founders, including myself, and the funders of Keiryopackaging all have a background in the fast-moving consumer goods industry, more specifically in one company called AB InBev. And as you know him, Roberto Johan, the CEO of our company, was head of packaging innovation at AB InBev a while ago when there was a big push to develop PET for beer, not for Western Europe, but for other markets. And from that perspective of being, you know, responsible for the innovation for a large FMCG company, he made this global perception that, you know, if you want to have a relevant sustainable innovation, you need to square a few challenges. First of all, you need a technology that reduces the carbon footprint, that increases the sustainability, we all know that, but also that is cost efficient, because cost is a very important dimension in our supply chain. And if you really want to have impact, you also need to do something that can be scalable. And to meet these criteria, well, he said, like, you know, maybe it would be better if you were in a position to leverage existing infrastructure that would address the challenge of CapEx. That is, you also have to be mindful of the technological complexity, but also of the regulatory complexity. And I think the people at PETCORE know very well how much regulatory complexity there is. So if you can avoid that, that's also, that would be a good driver for the innovation, and ideally a solution that can apply to multiple categories of polymers. If you take all these challenges, he came with the what if question, and his what if was, well, what if the slides would change faster? That would be a good what if. And the second what if there was a process allowed to extract more performance out of existing polymers? That would, if I go back to my previous slide, allow to use the existing infrastructure. You would not have to go to new regulatory validations. And because you have more performance, you will likely to have something that is cheaper and that is scalable. And nature tells us something very simple, is that the performance of a material is defined by its morphology, the balance between crystalline and amorphous materials and how they are organized. And nature also gives a very good example of what that actually means. If you look at the molecule of carbon, if you have carbon with a low level of molecular organization, you have coal. If you have the same carbon with a high degree of molecular organization, you have a diamond, which is better when you are in the market for an engagement ring. But fundamentally, it is the same material. What we have done is that we have taken this principle and we have used it to convert the level of organization of polymers. It's a processing tool, and during the processing phase, the polymer is pushed through our device, and what will happen is that the low level of organization will be transformed to a higher level of organization, meaning a different structure of crystals, a different way the amorphous components are organized. And this technology is based on a well-established science, which is called the science of flow-enhanced nucleation and induced crystallization. And this science tells you that there is an ability of polymers to alter their crystallization kinetics and the resulting microstructures when they are subjected to deformational flows. Now, I just want to open a caveat here. When we talk about crystallization, we've seen that there is often a misunderstanding because crystallization is not always seen as a positive development in industrial processing. And there is a clear difference that needs to be understood between the best known crystallization, which is quiescent crystallization, and the crystallization that we leverage, which is flow-enhanced nucleation and induced crystallization. If you have some time, go check on our website. Our colleague Edita Niemczyk made a very comprehensive paper that explains the difference between the two sources of crystallization. With flow-enhanced nucleation and induced crystallization, what you do is that you control the flow to stretch and align the polymer chains to create a more uniformly spread nucleation and generate crystalline structures that are smaller, better oriented, and better integrated in the polymer matrix. Whereas when you have quiescent crystallization, you have spot-like places of crystals that are not what you are seeking to achieve. What we have done is that today we have demonstrated that we can apply this process to the field of the PET injection stretch blow molding of bottles. And if you look at the performance of a PET bottle, you're looking at mainly three buckets, which is the top load, the barrier properties, and the thermal resistance. And the amount of material that you will use will be defined by the level of performance that you have to achieve on these three items. Today in our development, we have demonstrated that using a similar type of resin and on standard machinery, we can improve the thermal resistance of the blown article, and we can also improve the various barrier properties, whether it's oxygen, water vapor, or CO2. The way this materializes, if you put it under a microscope, what you have here is, if you have the current process, you have on the picture, you see this represents the morphological structure of a PET bottle. The blue rounds are crystals. And in the current process, you have crystals of a certain size that will define the passage that molecules of oxygen and CO2 and water will travel to go through the membrane. When you use the Keiryo technology to inject the preforms and then when you blow the bottles, you will see that the size and the amount of the crystals has changed. We have more crystals of a smaller size, and that kind of creates a more difficult passage for the various molecules. It's like a fishnet. You know, if you have a fishnet and you reduce the size of the mazes, it becomes much harder for the molecules to pass through. And that's how you improve the performance of the material. I will explain you first how we managed to observe this, because this was in itself a challenge. Yes, so to measure this change in morphology, which leads to an increase of performance, we had to develop various evaluation protocols. As a way of an anecdote, I can tell you that a couple of years ago, we shared our technology with a major FMCG that used our technology to inject carbonated soft drink bottles. And they measured a barrier improvement of the CO2 of 15%, 1.5. And they said, oh, we could lightweight the bottles by the same amount. But they didn't see any change in the morphology of the material. So they were very puzzled about how we got about this. And rightly so. So we had to develop, next to measurements that are optical and thermal, we also develop protocols that are based on a nuclear magnetic resonance to define the size of the crystals, and also about an X-rays to identify the orientation of the amorphous material. And that allows us to have a picture, what we call the picture of the beast, which is basically seeing that, you know, when we use our technology, the morphology and the level of organization of the material is changed. We also obviously measured the performance, and for the sake of the presentation, I will go fast of that. But basically what we do is that we benchmark preforms that are bottles that are made of preforms that are injected without our technology on the same machine, on the same resin, and then we inject with our inserts, and we compare the difference, and we see an uptick in the various barrier performance, whether it's water vapor transmission, the oxygen rate transmission. Everything is done at the University of Hasselt that has the right tool set to do these evaluations, but also of the thermal resistance. And what we've seen is that using our technology, you get thermal performance for a generic resin that is quite similar to what specialty resins are achieving. What this leads to is, if you have an increased performance that is yielded by a better morphology, it unlocks two ways to create value. Either if you want to maintain the same level of performance, you will be able to achieve it using less material. And so that will allow you to have, for each bottle, less CO2, better circle of better footprint, but also a reduced use of raw material, which is thereby a cost saving. Or you can have the same amount of material, and then you will have better functional performance, which can impact the shelf life of your product if that is what you are seeking. But there are basically two pathways. Now, what we have achieved and what I just demonstrated so far is not the result of a test in the lab. This is the result of trials that have been executed in an industrial environment. On the picture here, you see the picture of the actual site where we are doing our trials, which is the factory of PDG Plastic, which you might know. PDG is a French preform and bottle manufacturer that's based south of Paris, and we have been working with them now for a couple of years. And when we do our injection cycles, we use commercial grade resin, whether it's virgin or recycled. We do our trials on their standard machinery and within the remits of what the machines is supposed to do. And the machines are operated by their people. We add QCs because we are in a development phase, but the aim there is to demonstrate that this technology can work in an industrial environment, that it is not changing the conditions of the machinery, that it's not impacting the production cycle. The only component that we actually change is that we retrofit a 3D printed insert, and there you have a picture of one of our older models, into the hot runner of the machinery. It is a 3D printed insert. What does it mean? Is that we can design it exactly to fit different types of hot runners. And because it is 3D printed, it's fairly cheap to manufacture. Today, in the small numbers of preforms that we produce for trials, we are under 200 euros for a preform. If you scale that up, you will have much lower prices. And that allows us to claim that this is a technology that is intrinsically low cost, and also that can have a global rollout. Why? Because if it works on one machinery, it can, at PDG, it can work in machines in Milano, in South America, wherever you want. We all know that the types of machineries that are used to manufacture inserts, preforms, are fairly similar. It's also a low capex because we, as a company, do not need to build a production facility. Today, the 3D printing industry that exists in the world has the capacity to produce enough of these inserts for the whole PET ISBM industry worldwide. So it's a no capex for us, but it's no capex for our customers. The fact that we are, and well, I'm getting ahead. Just I wanted to summarize what I've said here. So today we are not market ready, but we have demonstrated that this technology is validated in an industrial setting. And what we do is that we multiply the validation points to get to a commercial level, and the validation points go about the validation of the platform and the validation of the performance. The trials at PDG, we first did trials at the monocavity machinery because they wanted to be sure that we were not damaging their machines. Once they were confident enough that this was working, we moved to multi-cavity. But also we've demonstrated that our inserts can process the standard resins that are being used on the market. We have already done more than several 100,000 shots, so we know that the inserts that we use have the right longevity and they maintain their performance over a long period of time. And in Q2 of this year, we will start doing what we call bespoke trials, is that we will start doing testing on bottles that are currently in the market and used by one of our clients that is interested in knowing, how this technology will work specifically for some of their packagings. In terms of performance validation, we have now a very strong capacity to demonstrate and to measure the morphological changes that we generate, and which are the source of the functional performance improvements. We have already measured a number of performance improvements, but this is an ongoing process. We work through testing cycles, and every time we do a cycle, we see an improvement in the morphological changes and then also in the performance. But we haven't today reached the final limit, the final objective, or we don't know how far we can go into performance improvement. The only thing that we know is that what we have measured so far was deemed by some of our customers as very market relevant. Now, this is where we are. And because, as I said, it's an asset-light company, the main asset of Keiryo is the know-how that enables us to define the conditions under which we can trigger the onset of the flow-enhanced nucleation and induced crystallization, and how we have to design the insert that is retrofitted into the machinery. It took us quite a while to build the modeling tool to be able to do that. And there is a lot of know-how there that we keep totally in-house. And the main asset of Keiryo is the patents that we have. Today, we have 3 families of patents that are very broad in their geographical scope. We cover Europe, the US, but also another 30 odd countries, because we wanted to reflect the footprint of the major FMCGs. And also we are adding patents. We are now at the end of March. By the end of April, we will have a 4th family of patents that cover an additional application, because one of the fun things when you do development, sometimes you discover new applications that can also be very useful. And so while we were doing the trials at PDG, they said, oh, maybe you can also solve that problem. It turned out to be very successful. And so now we are adding a patent on that item, but I will be able to disclose more information about that in a month or so. And I pushed on the wrong button. Yes. So the fact that we are an IP-driven company that doesn't have assets also influences the commercial model that we envision. And we describe it as a pay-as-you-benefit. Basically, we will give licenses to our technology to our customers, and the license will be a portion, the price of the license will be a portion of the savings that our technology is generating. So there is no upfront payment to have access to our technology other than the sale of the Keiryo products. But as I mentioned, this is these are small amounts, so it's not a capex, it's an opex. but it will be a licensing model where you pay when the technology generates benefit to your supply chain. Our team is a mix. We are based in Luxembourg, and that was a wish of our shareholders, because being an IP company, the IP policy of Luxembourg is probably one of the most interesting in Europe. We have a mix of full-time employees, the day-to-day management, and some engineers, and then we also work with external consultants that are, I would say, high-level experts in their domain, whether the IP, which is a big investment, or we have a broad support of scientific leads, like the Professor Savas Hatzikyriakos, who is one of the most renowned experts in polymer rheology. But we also work with a wide network of knowledge centers, like the University of Montreal, who does the characterization of the preforms, the University of Erlangen, but also the EPC in France, that were instrumental in developing several components of our technology. And as we move forward, we will onboard more in-house people, but that was a model that allows us to be, on one side, very lean, but also to tap into the best minds to develop our science and our technology. We have the chance to be supported by shareholders that have a very strong experience in FMCG, because they were CEOs of large companies, or they are majority shareholders of large FMCG groups. And that's why they really were very supportive of this concept, where you improve the sustainability, but you do it in a system that is cost relevant, because from their perspective, they understand that this is paramount if you want to be able to deploy something at a large scale. It's not only about improving the sustainability, it's also about being cost efficient. We're not market ready, but we already have signed various types of collaborations where we enable future customers to have a much more detailed access to what we have achieved so far than the very short presentation I give you here. And this is a very good way for customers to make an evaluation, of all the components, the scientific basis, how we did the industrial de-risking, what are the results that we observed, and that allows, to validate the relevancy of this technology for their packaging mix. And then we move to bespoke trials, like we are going to do into the next quarter. And so that's the last slide of my presentation. If you have to remember one item, is we have the pathway that performance follows morphology, and that allows us to have a solution that doesn't require a CapEx expense, that is inherently highly scalable, and that will yield a margin positive sustainability solution. I will add that we focus on PET, but the underlying science and the patent base that we have taken also mean that this technology can be applied and developed for other materials than PET, whether they are fossil-based or bio-based. As a matter of fact, science tells us that bio-based material will be extremely responsive to the concept of flow-enhanced nucleation and induced crystallization. And with that, I have completed my presentation, and I thank you for your attention.
Thanks very much indeed, Tangui. It's impressive what you showed, and it is impressive the fact that by changing the morphology, then you can change the performance of the final product, and that's something which is in a way unique. And when you say it is the company is IP driven, yes, but I think that it is very soundly, say, driven by scientific findings and scientific, say, research. Okay, questions are coming. Okay, the first one from Leaf, who left, by the way. It is not a question, but basically just a suggestion that Keiryo is indeed very much involved in the enzymatic recycling. It is what we have been discussing in the first part. There is a question from Sylvia. and it is related to the Keiryo technology. So which packaging fields can the Keiryo technology be applied to potentially? I mean, potentially, which is the field where this technology can be applied? It is only for injection molding, or it can be also applied to other processing techniques?
So it can be applied to other processing techniques, but the focus of our development today is the injection stretch blow molding. But if you look at the underlying science, it is any processing technology that needs a flow and that generates a flow would be subject to the science of flow enhanced nucleation and induced crystallization. And we have the modeling tool to design the inserts to apply to other processing techniques. It would not be the same insert as for PET ISBM, but it would be the same underlying principle. And I would say the tools to build a processing tool for other processes exists. It is just that when you are a company like ours, you focus your resources on one item. Now, this being said, we've had many questions from other industries to see whether the technology would be applicable. And we're always open to discuss, collaborations and how we could do that and how we could tap into the existing knowledge that we have acquired to start a different development track.
Good. Great. Thanks. And since we are touching that point, you mentioned that, of course, I mean, you are going to expand the cooperation with the potential customers, and therefore also your collaboration program is going to, say, expand, increase, being boosted. Can you elaborate a little bit more? I mean, which is the customer portfolio, if I may call it that way, that you are targeting? Because clearly your technology seems to me very versatile. So, if you can elaborate a bit more on that.
I think you use the very right word. It's versatile. It will depend on the dynamics in the supply chain. We have already signed contracts, evaluation contracts with large FMCGs that are interested by the technology for their packaging mix. And by taking a license that allows them to have some freedom of their supply chain and see how they deploy the technology. Now, this is not necessarily a model that will work for everyone. We know that the dynamics of the supply chain will depend on the size of the stakeholders. As mentioned previously, we at Keiryo, we all come from AB InBev, which was a company that was very strong into putting, pressure on its supply chain and go through systems of, see-through margin analysis. And I think you've been on the other side of that. But depending on the size of the stakeholders, the license might be in the hands of the converter. PDG has a number of very small customers, and there you would have a different model. What matters for us is that our technology creates a margin, and then you have to find the right model to capture the margin and to deploy it. And that's why the licensing model offers a great flexibility to adapt to the various market dynamics.
Thank you very much. And Ben, I think you already answered in your presentation, but just to be sure that I captured rightly what you said, this technology can, of course, apply to different kinds of polymers, and also, of course, the bio-based polymers, because ultimately bio-based is just differentiating the polymer based on a different source, different from say, the fossil. But basically, I think that you can confirm that your technology can indeed apply to our, say, polymers when it comes to produce packages, right? I think the Tangui was frozen, probably.
Oh, sorry, the question was for me?
Yeah, I mean, sorry. No, well, more than the question was just to be reassured that indeed what I captured in your presentation is right. So what I was saying is I understood that your technology can be applied to other polymers other than PET, can be used in many different fields.
Yes.
biopolymers as well, because biopolymers, the difference between biopolymers and standard polymers is only the nature of a feedstock, which comes from either, non-fossil or
Yes.
fossil sources.
No, sorry, I thought you were the question was for someone else.
Yeah.
Yes, no, in theory, if you look at the science, it works with biomaterials. We had long conversations with PLA producers because
Mm.
PLA has performance challenges in terms of heat resistance. And so they saw technology as not a way to reduce cost, but as a gateway to applications that are today not possible with the current way of crystallization of these materials. So yes, we also talked, with wheat algae-based materials that want to venture into new applications, and they also hit performance challenges. And so they're very interested by that. The difficulty is that to do that, you need to have a very good understanding of the rheology of your material. And that is a knowledge that is very often between the material producers and the processors. So no one really controls or has a full understanding of that. And we've seen that some seaweed producers, for instance, don't fully understand their material. If you don't fully understand your material, it's hard to apply the technology.
Yeah.
In principle, yes, it is possible. I would say the main barrier is a barrier of resources to look at that.